Recording, turning the volume, and we're off. Okay, welcome back to CS 152 252A, lecture 4, even though the slide says lecture 3. Before anyone asks, the lecture slides for today are not posted because we're exactly one lecture behind. So open the PDF for this Tuesday and you'll see today's slides. We're, as of right now, I'm hoping by the end of today to be 25% behind. At the end of last week, we were 50% behind. So this is trending in the right direction. But that is just a heads up. We do have a few administrivia. I was going to say for a second that I didn't think you did. Homework 1 is out. So have fun. It'll be due in 2 weeks on February 7th. Go to discussion, go to office hours. Everyone is here to help. The lab is not quite out yet. We're currently patching up some issues with it, trying to get it to work on your all's local machines in addition to you being able to run it on EDA servers, because we are worried about server load given the class size and who else is sharing the EDA servers. And we've just found some wrinkles in doing that. So suffice to say, it is on its way. It is not out yet. As soon as it goes out or goes live, you'll have exactly 2 weeks to do it. So you're not losing time. And arguably it being a little bit late is good from it'll be offset from when the homework is due perspective. Any other administrative questions before we get started? We're doing less and less of this as the lectures go on, which again, I think is trending in the right direction. Okie dokie, let's do pipeline. All right, so then we have the usual keyboard problem. It's going to work. Cool. Okay, last time in lecture, the focus was on microcode orchestrated, non-pipelined data paths. We expounded on some of the benefits of microprogramming, namely that you could implement an arbitrarily complex ISA with a relatively simple microarchitecture, and in particular that the microarchitecture's complexity could be made to be independent of the complexity of the ISA, as long as you're able to accommodate a sufficiently complex microprogram, which is to say you have a large enough microprogram ROM. Now, just to kind of end or take microprogramming a little bit farther and tell you where we're going. So when people started microprogramming, they realized that it was this wonderful paradigm where you could build complex ISAs. This was great because we didn't have compilers that could deal with less complex ISAs. So it really took off. It really took off. People came up with a number of ways to optimize microprogrammed non-pipeline data path architectures. And that was what got us into the last part of yesterday's lecture, where we were talking about optimizing the microprogram ROM encoding both in the vertical and horizontal direction, vertical, horizontal microcoding. And at the very end, we talked about nanocoding. This continued for some time. We're going to end microcoding or microprogramming today, talking about some of the later stage innovations related to microprogramming. And then we're going to tilt our head a little bit and see how microprogramming kind of became spontaneously RISC. So what people realized when they had sufficiently added complexity to the concept of microprogramming was that really what they wanted was RISC, which was a different style of ISA, and that ISA led to a different style of high performance data path design, namely the hardwired pipelined data path that you all learned about in 61C. And so that's going to be our transition into pipelined data paths and RISC, which is kind of the main topic of today's lecture. So just bear in mind the trajectory here. We started with microprogramming, a clean paradigm for dealing with complex ISAs. Once you take it to its limit, you realize what you want actually is RISC. And when you want RISC, you want pipelining. And that will be what we cover today. But before we get there, like I said, microprogramming really took off for a number of years. Here's a number of different microprogrammed microarchitectures falling under the IBM 360 umbrella, just to give you kind of a sense for what these machines looked like. So these different microarchitectures, some of them had different data path widths. Remember that you can implement the same ISA regardless of what your data path width actually is with microprogramming. A Turing machine would be an example of a 1-bit data path, if you will. The micro instruction width in bits kind of varied as a function of data path width, kind of like what you'd expect. The microcode size was quite substantial, as you can see. So we were dealing with a small handful of RISC-V ISA level instructions that were microcoded into a few ops each yesterday or 2 days ago in lecture. But you notice here that the microcode size to support the IBM 360 ISA is on the order of kilo micro instructions. So that kind of gives you a hint as to what this ISA looked like. More complex than the RISC-V ISA that we were dealing with 2 days ago. And here are just some other facets of the microarchitecture. Microcode store cycles, memory cycles. Interestingly, if you compare these numbers to memory access times today, they are higher, but the difference between then and now for memory access time is not nearly as large as the difference between, say, the time propagation to go through a 2-input AND gate in like modern CMOS. Like that time has dropped precipitously as CMOS has scaled down vis-a-vis Moore's law over the past 75 years. And then you have the rental fee, just to kind of give you a sense for what these things cost. So here was a technology for implementing the microcode ROM, a punched card with metal film, interestingly based on capacitive storage. So just another kind of nifty use case for microprogramming that we didn't discuss 2 days ago is emulation. If anybody has used things like Kimu and other like emulation engines, you've experienced the magic of emulating an ISA for one machine on another machine and emulating that whole thing on yet another machine and going all the way down. So this had both interesting from a just Blackmagic Ninja perspective aspects to it, and also from a commercial perspective. So in the early days, emulation was a way of stealing customers from one company to another. So you have IBM. IBM had the 1401 architecture and the 360 series CPUs. And this other company, Honeywell, noticed that there were all of these programs written for the IBM 1400, and it created a microcode emulation engine called the Liberator for running programs written for that microarchitecture on their own microarchitectures. Because, hey, why not? Writing software is hard. IBM retaliated with the 360 by creating proper microcode emulation engines from their old ISAs to the 360 ISA. And interestingly, one of the programs that people typically wanted to emulate was a program that simulated the performance of an IBM 650 microarchitecture with the IBM 650 ISA. And because of this emulation, we're now emulating this program, which is a simulation on yet a third machine. Again, turtles all the way down. So suffice to say, microprogramming thrived in, yeah, question. Simulation versus emulation, good question. So emulation refers to running a program written in one ISA on a microarchitecture that natively supports a different ISA, potentially. This is like running code compiled for Mac OS on like a Windows PC, for example. Simulation is the process of simulating for usually the purposes of analyzing efficiency, performance, things like this, a microarchitecture plus ISA on some machine. So what you'll be doing in the labs is simulating. You'll be simulating the performance, energy consumption, things like this of various pipelines that you design on the lab servers, which are whatever, like running Intel or like using like Intel processors. Good question. Okay, so microprogramming thrived for a number of years. We had fast ROMs, much faster than DRAM, so it made a lot of sense to just have these large microcode ROMs. We had complex ISAs, simple microarchitectures. We could implement very complex, possibly corner case instructions without changing the data path. I've mentioned this before, but a good example is something like floating point, which you can emulate using the small set of operations that we discussed 2 days ago in lecture. This is very good for fixing bugs. If you discover that you've implemented one of your ISA instructions incorrectly, if your data path is hardwired, then you're in a heap of trouble. If your data path is orchestrated by a microprogram, as long as the control logic that allows a given micro instruction to orchestrate the pipeline, as long as the bug is not there, as long as the bug is in the sequence of micro instructions that you're using to implement an operation. So for example, going back to the add from 2 days ago, if instead of implementing an add, you accidentally implement a store or some crazy other thing like that because you've set an opcode incorrectly, as long as you have a backdoor to update the microcode ROM, I know that's kind of a paradox because it's a ROM, but bear with me for a second, then you could at least in principle patch the bug without taping out new hardware. So there was a path towards reprogrammability, at least conceptually, and ISA compatibility across different microarchitectures. And this had all sorts of cool use cases. And just a kind of note, except for the cheapest and fastest machines, all computers were microprogrammed. So this really took over the world in the 60s and 70s. Now, naturally, when you push this idea, you start seeing a natural progression of ideas which ended up repeating itself once we went to modern RISC, CISC style pipelines in the 90s and the 2000s, but just in the micro code domain. So as you kind of push this idea, eventually what you find you want to do is implement ever more complex instructions using these micro operations. Eventually, these become so difficult to implement that dealing with things like bugs in your microprograms become more and more of a problem because there's a fixed rate of bugs written per number of lines of code. If you're a software developer, you've probably heard that adage before. In addition to that, and because of there being the potential for bugs, you'd like to be able to write your microcode ROM as opposed to just read it. So all of a sudden we're asking for new features, being able to write your microcode ROM at like some granularity in time. In addition to that, you find yourself wanting more sophisticated software constructs. So if I tell you that your ISA has an instruction for performing C code compilation, that's completely bogus, but I'm just using it as a proxy for a very complex operation. Given a program in, compile the whole program and spit the program out. If you try to code a C compiler in microcode, you're going to want all of the software infrastructure that we're familiar with and spoiled by, such as the ability to call subroutines, add headers, all of these sorts of things. And that's what people started wanting to add support for in their microcode. So the complexity was starting to blossom here and arguably get out of hand. Now, not to talk about the subroutine part, we're not going to really talk about that further, but I do want to say something about the ability to write over contents of your microcode ROM. So we've called it a ROM, a read-only memory, up till this point. As SRAMs, which could be dynamically written to, became less expensive relative to ROMs and the complexity of microcode increased, these two came together and people started proposing mechanisms for writing over their microcode ROM, again, in the spirit of fixing bugs and things like this. Really hardcore programmers used this technique kind of like, you can think of it as like operator overloading from, if you've if you're familiar with languages like Ruby, on steroids, where you can literally take any ISA level instruction and reprogram its microcode so that you can do a potentially completely arbitrary different operation in place of the ISA level operation. And I mean, this feature exists in some languages, dynamic languages today, like Ruby, for a reason. For example, if anyone has taken group theory or abstract algebra, mathematicians typically deal with numbers and that have particular algebraic structure, like numbers where there's a plus operator, there's a multiply operator, plus is commutative associative, times has its like own set of properties, but depending on exactly what the group, or as they call it, the ring is that we're talking about, the implementation of the plus or the multiply might be very different. For example, plus could be like just adding two numbers together, like what we're familiar with, or it could be overloaded to implement something like a output the max between the two inputs. And that's fine as long as it satisfies, again, the certain abstract properties like, is it an associative operator? So some programmers were using this ISA instruction overloading to implement some of the features that now we're spoiled by like dynamic languages like Ruby. But suffice to say, this started getting quite complicated, and it defeats the purpose of having an ISA in the first place. When you have an ISA, you're expecting a particular semantics for each ISA instruction. If you can just overload that completely and freely, then what's the point? There wasn't much software support, for example, compilers backing this reprogrammability, so it didn't really take off. But I wanted to mention it because it was, in fact, briefly a thing. Okay, now, at this point, complexity was getting to a point where the intersection of technology was starting to push us in a different direction. So as RAM, random access memory that is readable and writable, was getting cheaper relative to ROM, one can interpret that as an excuse to make your microprogram ROM writable, or you can interpret that as a motivation or a suggestion that the whole microprogrammed paradigm is just completely wrong. And that really what we want is an instruction memory that you can freely change per program, as opposed to a microcode ROM, which is constrained to implementing the ISA instructions. In addition to that, at the same time, again, because of technology changes, there were numerous things that we could now do in the microarchitecture to alleviate or change the game in terms of how we built these machines. So back in the early days, we had these very simple bus-based architectures, but as technology was progressing, people were proposing pipelining, caches, buffers, ways of performing simple operations like reg-to-reg operations, like the ad that we saw from 2 days ago, much more cheaply than the way that we did it. 2 days ago, we went through something like 8 steps to perform the ad. Fetch 0, 1, 2, add 0, 1, 2, 3, 4, 5, something like this. And just because of technology changes, these operations could go very fast. And so the prospect of doing them in a microprogrammed way was becoming less and less attractive. So that kind of started our shift away from microprogramming. But before we chipped away, I just wanted to show the slide. This is some of the microcode for an old VAX machine. You can absolutely offline read this, and it should make sense. This is just the low level, the micro operations that are implementing different VAX instructions. And before we shift away, I would like to say that microprogramming is, even today, far from extinct. We just use it a little bit differently. So it played a crucial role in these architectures in the 80s. It's still used in modern machines today. It just takes on a little bit of a different form. So if you run an AMD or an Intel processor, it's running the x86-64, which is to say 64-bit wide instruction set. This is a CISC ISA from back in the 80s. There was a huge gamble on Intel's part, which majorly paid off, which is that they should not, under any circumstance, change their ISA for backwards compatibility reasons. And so we are still blessed with x86 today on both Intel and AMD parts. And just like in the old days, they're not implementing these CISC ISAs using hardwired fixed data paths, they're micro-coding them into simpler RISC-style operations. But the way they're doing it is a little bit different. The way that it works today is you've got your x86 ISA, and if you look through that ISA, there will be some familiar names like add and sub, things like this. But there are also some crazy instructions, for example, memcopy, and that's not even one of the craziest ones. And don't ask me to remember their acronyms. One of them is AAA. I cannot remember what this instruction is for the life of me. I believe that there's also a double A. Suffice to say, there are instructions that look familiar and there are instructions that look exotic and seem a lot more complicated. And so the way that x86 gets all the benefits of modern microarchitecture and RISC, but without changing their ISA, is they have a decode stage towards the front of their pipeline, which as the CISC instructions are coming in, performs what is hopefully in the common case a very light translation from the CISC instruction to a RISC-like counterpart. For example, if there's an x86 add instruction, it can sometimes be just emitted as a single add instruction RISC style and sent to a RISC style pipeline. And if there is a very complicated instruction like AAA or something, it's broken up into successively more micro-ops. And so the idea here is you get your backwards compatibility, you get your RISC style pipeline, modern pipelining techniques, and in the common case, you don't lose performance for using this CISC ISA. So micro programming is still present in today's architectures in that form. I'll note, if anyone is interested in exactly how x86 microarchitectures break x86 instructions down into micro-ops, and remember, micro-ops are like a below ISA proprietary level thing. We shouldn't really know what they are. There is this wonderful resource called uops.info. This started out of an effort to reverse engineer modern processors by a person in Europe named Agner Fogg, who is a lovely patron of the arts, I call him. He did an extensive analysis showing exactly how on a set of microarchitectures, each instruction was broken into micro-ops, and furthermore, what each micro-op uses in terms of pipeline resources. We'll get into out-of-order execution style architectures later in the class, but suffice to say, there's a number of parallel execution units, and so a question is, for a given micro-op or op, what execution unit does it occupy? So uops.info is kind of taking his work, taking the flagpole, so to speak, to the next level and really systematizing with automated experiments, ways to reverse engineer, push button a given Intel or AMD microarchitecture to break down and figure out through timed experiments exactly how instructions are broken into different micro-ops. So if anyone is interested, I fully suggest that you explore this resource. It's just super cool work. And just one more use case. Well, I've already kind of like mentioned this before, but I'll say it again. A use case which still prevails today in terms of using microprogramming is to patch bugs. I said patch bugs, but the more modern incarnation of this, or the one that gets more press, is coping with security vulnerabilities in microarchitecture after the microarchitecture has shipped. So I spend a lot of my time thinking about problems like this. There have been many security vulnerabilities. We will spend some time at the end of the class talking about what exactly that means. But suffice to say, if you have a security vulnerability, like call it a buffer overflow implemented in your microcode, it's a lot easier to patch it out if you have microcode as opposed to hardwired control. It's not exactly what the modern security vulnerabilities are, but it kind of gives you a flavor. Okay, so that's how microprogramming is used today. I want to motivate a set of experiments that were performed in the 80s, late 70s, early 80s, which motivated our move away from microprogramming. And I just realized, okay, great. Pause recording, stop recording. Thank goodness. I'm always paranoid that I forget to turn the recording on, but it looks like we're good. Good. Several experiments that motivated quantitatively our move away from microcode and into RISC. So the first was, and naturally my keyboard's not working again. Okay, the first was done by John Koch and a group at IBM, where what he did was very interesting. He took a micro-programmed, or he took an ISA implemented by the 801, and he performed kind of manual compilation using that ISA, and only when he was compiling code used a very small percentage of the ISA. So the ISA, like I said, the number of instructions in the microcode ROM is like in the thousands. The ISA is complicated. And so the question he asked was, if I only use a very small subset of the ISA, what does the code look like? How well does it perform? Recall from when we introduced the Turing machine that you don't need many instructions to achieve Turing completeness and encode any program. And so commensurately, you could use a very small percentage of the ISA and be able to encode any program that you wanted. And what he found was that the code that he wrote was actually faster. It only used a very small percentage of the ISA, but it was actually faster. A similar experiment done by Joel Emmer, and Clark at DAC. Aside from performance bug removing an important performance bug in the VAX, found through looking at a bunch of programs that despite the fact that a small percentage of VAX instructions were responsible for most of the microcode, if you look at the amount of time in an actual program that those instructions are actually being used for or are like running for, it's exceedingly small. So there's like a large amount of the microcode ROM contents which is not being used. So it's kind of like the same result as what John found at IBM, but looking at it through a different lens. And then finally, micro store RAM control store unified for cache RAM. Oh yes. And finally, there was this VAX. It was just like a VAX machine whose characteristics started to look kind of absurd to people. The observation was, okay, around this time, microarchitecture was becoming more sophisticated, and we were getting things like read-write cache to decrease memory access latency. The microstore RAM, it was a RAM at this point, but it was being used to house micro operations, was much larger than the cache RAM. So like we said, you can take a very small pipeline, and as long as you have a sufficiently large microcode ROM or RAM, then you're good to go implementing any ISA. But it had now gotten to the point of being ridiculous, where the microcode ROM or RAM was a significant percentage of the on-chip area. Okay, so these experiments suggested that we had taken the idea of microprogramming too far. And they helped develop a model, a way of thinking about processor performance that is still in use today. This slide calls it the iron law of processor performance. Have you seen this before in 61C? Great. It's also called by other names, like the processor performance equation, but they're the same. What it says is that the time of a program is broken into three pieces. The first is the number of ISA level instructions in the program. I say ISA with boldface to distinguish ISA level instructions from micro instructions. We're going to call it ISA level instructions just to be clear. The second is the number of cycles on average per ISA level instruction. And the third is the time per cycle, the clock frequency or the clock reciprocal of the clock period. And what you probably learned in CS61C was that instructions per program, and you can infer it from our discussion so far, that instructions per program depends on the source program, clearly, the compiler technology, which influences how the source program is compiled to ISA level instructions, and the ISA itself. You could have a very simple ISA, more instructions per program, more CISC ISA, and fewer instructions per program. Cycles per instruction depends on the ISA and the microarchitecture. if I give you an ISA with very complicated instructions, like a CISC style ISA, that's probably going to mean that you have more cycles per instruction. But clearly, this is also a function of how sophisticated your microarchitecture is, whether it's bus-based or whether it's pipelined or something like this. And then time per cycle depends on the microarchitecture and the underlying technology, like the underlying transistor level technology, which dictates things like how quickly can you propagate the inputs of a 2-input AND gate to the output in nanoseconds. And what's interesting about this model is that the first term is a function of program, source code, everything in the software stack down to the ISA. The second term is a function of the ISA and the microarchitecture right below the ISA. And then the third term is a function of the microarchitecture and the technology. So you can take the stack and you can break it up into several pieces, and you can analyze just through changing one in a kind of point-wise fashion how that's going to influence your program's execution time. So this was how people started thinking about processor performance as the process of evaluating machines was becoming more quantitative, which was kind of pioneered in the late 70s and 80s, those experiments 2 slides ago, analyzing these microprogrammed machines. Okay, let's go into a little bit more detail on CPI in particular. So CPI for a microcoded machine. So this notation, inst1, inst2, inst3, we're going to use this notation where the rectangles with the thick borders are going to signify ISA level instructions, and the little lines partitioning each big rectangle with thick borders is a clock tick. So what this means is we have 3 ISA level instructions, and it's broken up or evaluated over this many clock cycles. And because we're dealing with a bus-based data path, each one of those cycles would correspond to a micro-op. So you take these 3 instructions and you calculate CPI by taking the clock cycles over the total number of instructions, and the ratio is your CPI. And this makes sense. You look at this and you see that for these 3 instructions, you're getting a CPI of something significantly larger than 1. We're going to be taking CPIs over large numbers of instructions, sequences of instructions that run, as opposed to single instructions. You'll see why in a few slides. There's several reasons that the CPI of a single instruction or a small number can be quite deceiving. Okay, so that's CPI. Now, about this time, again, so we have microprogramming, we have quantitative evaluation of microprogramming, we have a new paradigm for evaluating the performance of machines, and now we have technology making advances. Let's discuss these tech changes and what bit they flipped in designers' minds. So simply put, the main technology changes that were happening now was that by this point, everything was being implemented in MOS transistors. CMOS was taking over, and the cost of RAM was decreasing relative to the cost of ROM. So RAM was becoming cheaper. Logic, as it moved into metal oxide semiconductor transistors, was becoming cheaper. So cheap logic, faster RAM. This is exactly the opposite of what we had when microprogramming first started, which gave us the incentive for these kind of simple logic-based data paths. And so that kind of brings us to the epiphany that I'm not sure who had it. Some people say it was Seymour Cray, others say that it was other people. I don't know who kind of first had this epiphany, and I'm not sure whether, truthfully, it was someone staring and squinting at nano coded micro machines like what we were talking about last class. But the analogy kind of goes as follows. Recall from last lecture the nano-coded architecture. You've got a micro PC, you've got a microcode ROM, which is where you're going to read the next micro instruction from. You take the microcode ROM signals that come out and you shove it into a nano instruction ROM, which you can just think of as like a combinational logic function, which takes some inputs and outputs a bunch of control signals. And then you have your data path. And if you squint your eyes a little bit in the context of the technology changes from the previous slide, what this starts to look like is, well, instead of having a micro PC, why don't we just have a normal PC? Instead of having a microcode ROM, why don't we just use an instruction cache? Because RAM is cheap by this point. And oh, by the way, if we have an instruction cache, we can freely customize the instructions per program, as opposed to having this kind of like constrained ROM. And then the nanocode ROM, this lookup table, or like I put it, combinational logic. A good thing to keep in mind is that combinational logic and a ROM are conceptually equivalent. If you've ever used FPGAs before, an FPGA LUT, which is short for lookup table, is a way of implementing combinational logic as a ROM. So another way to look at this second lookup table is as hardwire decode, combinational logic that performs hardwire decode to feed the rest of what is now you'd think about as a hardwired pipeline. And this is exactly RISC. So once you have this epiphany, you realize that RISC is actually what you want. And this is how RISC as a concept originated. And so the idea here, to repeat, is instead of using these microcode ROMs, let's use fast RAM. We have it now. Let's cache within it instructions of user visible code. That way, whenever anyone writes a program or changes a subroutine, anything like that, they can just freely change it because the ROM is writable. If we use a cache-based paradigm where we're not constrained by the physical size of the cache to fit our program, because caches, recall from 61C, have fill, evict mechanics that enable us to emulate more quickly having a larger RAM, but with actually only allocating expensive RAM storage for a finite size. We don't have any restrictions on the size of our program, or at least they're significantly alleviated, and we can more easily modify things. Furthermore, let's use a simple ISA with a hardwired data path instead of a bus-based architecture. This is because pipelining the cost of registers had gone down in the past 10 or so years. And then finally, it's just easier to integrate. It's easier to integrate a hard-coded data path in with the rest of the system, a larger system, than it is with bus-based architectures. Buses don't scale. Okay, so that took off RISC. RISC was, like I said, RISC and MIPS being one of the first RISC concrete ISAs. They all go by different names. MIPS sometimes stands for millions of instructions per second, which is a clever marketing term. Sometimes it stands for microprocessor without an interlocking pipeline. RISC, likewise, some people call it reduced instruction set architecture as kind of an analog to CISC. Others call it really invented by Seymour Cray. So exactly where the ideas came from are a bit unclear. Suffice to say, Berkeley was absolutely a pioneer in helping the world wake up to this change in technology so that it could achieve adoption. So the first RISC chips, RISC-1, RISC-2, were both taped out at Berkeley. Here's a die shot of both of them. After you've done VLSI design, you start to appreciate how elegant this layout is. This is a really, really nice design. And that brings us back to, okay, now that we've kind of made this transition, where's the efficiency payoff going to be? So going back to the iron law of processor performance, we have the three terms as we had before, and now we can kind of bin the different data paths and ISA styles, control styles, into several categories. So at the bottom, we have our microcoded ISA, or a microcoded data path governing like a CISC-like ISA. And on the one hand, going back to the processor performance equation or the iron law of performance, the clock cycle time of such an architecture could be relatively short. There weren't any long paths. Everything was talking to a bus, so you could break up combinational logic in kind of a natural way. So you had short clock cycle times, short clock periods, meaning a higher clock frequency, meaning higher performance for time per program, which is great. The bad part is that the CPI is really high. The CPI is as many like micro operations, again, on average, are needed for a realistic instruction mix to evaluate a given program. It's like 1 micro-op per cycle, and every instruction, even simple like register to register adds, are broken into many micro-ops. So that was microcode's kind of downfall, a high CPI. On the other hand, you have like a natural RISC style pipeline, which you implemented a pipelined RISC-V in 61C. Did you start with a single cycle pipeline? Okay, great. So this is the first single cycle pipeline. CPI of 1, that's awesome, but the clock cycle time is long. It's as long as the worst case instruction in the ISA, which is potentially very bad. So unclear which of these two win. On the other hand, when we adopt some of the microarchitectural innovations, namely pipelining, to the RISC paradigm, that's where we start to see the win. We achieve short clock cycle time because we're doing pipelining and we're breaking up a long combinational critical path into multiple cycles where the clock frequency can be set just based on whatever the longest chunk of combinational logic for a given stage is. And the CPI is not 1 always per se, but 1 could at least conceptually or hypothetically get very, very close to 1. Getting close to 1 or achieving 1 will entail a lot of hard engineering effort, which is going to be the rest of the lecture. But at least in principle, it's possible. All right, so that brings us to pipelining. So now we're on to kind of like the main topic for today's lecture. So here is, some of this might be review. I apologize. We're going to go over it again. Here is your classic 5-stage RISC pipeline. Might as well be RISC-V pipeline. We have all of the things that we were doing before in the microprogrammed bus-based data path, but now with point-to-point interconnects between the stages as opposed to using this shared bus. The reason why this is now a thing, we haven't really changed the org. We've just replaced a bus with these point-to-point interconnects, is because registers had gotten cheaper. So pipelining means more registers. If registers are cheap, you can forego the bus, which was cheap in terms of wires, but who cares at this point, for these direct point-to-point connections. And we see all of the usual suspects, PC instruction cache, this is fetch. Next, between instruction fetch, the IR register, and the register read, we have decode, followed by execute, followed by memory, followed by write back. To avoid off by 1 errors in the following slides, I want to be precise about exactly where the pipeline stages begin or end, otherwise it'll be a little bit confusing. So where I've drawn these dashed vertical lines, what's important is that they align with a bank of registers. So you have a bank of registers that are at the output of the register file. For this reason, we say that the register file in memory is a synchronous read, which is to say, if I put an address in by the rising edge of clock cycle I get my data out after the rising edge passes of clock cycle I. I don't get it out sometime later in clock cycle I have to wait for clock cycle I plus 1. Likewise, I have a bank of pipeline registers separating the output of the execute stage going into the memory stage, so on and so forth. Okay, so with that pipeline in mind, I wanted to say one more thing about this pipeline. I don't remember what it is. I'll come back to it. Kind of like a cool aside. Okay, with that pipeline in mind, we're going to go over some CPI examples in the context of pipelining. So here is our microcoded machine from before. We have our instructions on the bus-based data path, and each one of them takes multiple cycles, so we have this bad CPI. On an unpipelined machine, we have something that looks like this. What we're going to do is we're going to set our cycle time to whatever the longest instruction is. So if you look at this example here, you see the longest instruction, instruction 3, is like yay long, and that's meant to be equal to this. And the amount of time that it takes to execute instructions 1 and 2 is elongated to that maximum time because that's what you have to do if you don't pipeline. You always have to take or set your clock period to the worst case path, the critical path in your digital logic. So what we get is we get 3 instructions. They're executed in 3 clock cycles, so it looks awesome. We have a CPI of 1, but the thing to keep in mind is that your clock cycle time is longer. So this is a long cycle. Not clear which of these two. Actually, I mean, this one would, or this unpipelined machine would be worse in this example than the microcoded bus-based data path, because at least you can optimize for common case, simpler instructions. A pipelined machine, on the other hand, gets the best of both worlds. You've got your instruction. For the purpose of simplifying the implementation, you have every instruction take the same amount of clock cycles. This is okay because you can overlap their execution and achieve something called pipeline parallelism. You have instruction 1, you break up its execution into fetch, decode, execute, all of those stages. Before instruction 1 is done, in particular when it enters into the second pipeline stage, you can fetch the next instruction, a cycle later fetch the next instruction, and they all kind of flow through. And the reason you might be looking at this CPI equals 1 short clock, CPI equals 1 might look a little strange here. Like what does the CPI mean when it comes to a pipelined architecture? So the terminology that we'll use for pedagogy is that you calculate the CPI from the time when the first instruction finishes to the time when the last instruction finishes. So you see that in this period of time from here to here, that 3 cycles finish, or 3 instructions rather finish. 3 instructions finishing in 3 cycles, you get your CPI equals 1. So you look at it from the perspective of when the first instruction writes back. And that's that was the cool aside that I wanted to mention. I remembered it in the context of this slide. So what you're exploiting when you pipeline your data path is a form of parallelism. Why do we call it parallelism? Any guesses? Yeah. Multiple instructions running in parallel? That's exactly right. It seems a little strange though, because usually parallelism refers to you running like multiple things at exactly the same time. It's like you take a program and you split it into 2 threads, you run both the threads at the same time, they run in parallel to each other. Any comments? Yeah. Yeah, that's certainly true. So I wasn't expecting an answer to my follow-up question because I left it very vague. But if you all are interested in viewing pipeline parallelism through a different lens, I encourage you to think of a hypothetical pipeline made up of an infinite number of pipeline stages. Ignore pipeline overheads, which are like setup, clock to queue, hold time, things like that. And just imagine this hypothetical pipeline with an infinite number of pipeline stages where because you're able to pipeline it infinitely, let's ignore hazards, which we'll get to in a slide, you can achieve a clock frequency of likewise infinity. If you view the pipeline through that lens, in that extreme, then pipeline parallelism actually becomes the parallelism that we think of at higher levels in the stack, more coarse grain, like thread level parallelism. Because if I submit a program to be executed on this infinitely pipelined data path, because the frequency is infinity, you'll be able to insert your program into the pipeline clock cycle after clock cycle at 0 time, or as the clock frequency goes to infinity, the amount of time that passes between when you inject the first instruction to the last instruction will trend towards 0. And at that very small amount of time after the first instruction finishes, your program will finish. So it actually, if you think of a normal pipeline as being one of these like diagonal waterfall diagrams, as they're called, where the instructions kind of flow diagonally. In the extreme case with an infinite number of pipeline stages, it actually reorients itself and you get something that looks very similar to thread level parallelism. This is not going to show up on an exam. It's just kind of conceptually a nifty way of thinking about pipeline parallelism. Yeah, sure. Uh-huh. Uh-huh. The stage inside each cycle. We're calculating the CPI based on the number of cycles that pass between when the first instruction enters write back, which is here, and when the last instruction enters write back. So it's 1, 2, 3.
But how does the pipeline?
Good question. In the unpipelined machine, your clock cycle is this. Sorry. So 1 cycle, 1 instruction. 1 cycle, 1 instruction. 1 cycle, 1 instruction. 3 cycles, 3 instructions. CPI equals 1. Yeah. But again, one of the morals of the story is you have to be very careful when dealing with the processor performance equation, the iron law of performance. It's not good to look at any subset of the terms. I guess they're on the previous slide now. You have to look at all 3 to understand your performance. Yeah. Mm-hmm. Yeah, very good. That's a good seg into the rest of the slides. Hazards. We're going to get to hazards in a second. You're absolutely right. This is best case scenario. And it's worth pointing out that even though we talk about hazards in the context of like these relatively simple 5-stage pipelines, we have control, data, structural hazards, we'll define them in a second. And then we go into more exotic architectures. I've used these scary terms, out of order, superscalar, speculative architectures. All of these ideas are just an attempt to get back to CPI equals 1, where normally it's the data hazard that is becoming harder and harder to deal with. Namely, like if you make a load, that load may not return for hundreds of cycles. And we had to come up with completely different microarchitectures for dealing with such extreme hazards. So just kind of keep that in mind. There's these terms that you may have been hearing for the first time in the past several lectures. There's nothing scary about what they're trying to do. They're trying to get us back to CPI equals 1, just like with this relatively simple 5-stage pipeline. Okay, to your point. CPI equals 1 is a dream. It's at least not something that we get for free. So, I believe this is also CS61C. Great. Prepare to see it again. So we have 3 reasons why we might not be able to achieve CPI equals 1. Structural hazard, which is that we have a hardware unit which is needed by 2 or more instructions and 1 instruction is using it, so we have head-of-line blocking. Another is, I guess the 2 others, are data hazards and control hazards, both of which you can group them under a similar umbrella because they're waiting for operands to become ready. So a data hazard refers to a case where I have an instruction, which, well, this is one example of it, is producing a result that is needed by a subsequent instruction, and the result is not ready, so the subsequent instruction must wait. A control hazard is the same thing. A dependent instruction is waiting on a result. It's just that the dependent instruction is a control flow instruction, like a branch or a jump. And the reason why we split these into 2 categories, data and control, is because it's useful to break them into 2 categories from a design perspective. Control hazards typically need to be resolved much earlier in the pipeline. And so the techniques that you must adopt in order to cope with them look very different than normal data hazards between, say, arithmetic instructions. And so if you don't deal with these, you have a CPI of greater than 1, which is bad. We really want a CPI as close to 1 for any possible instruction mix, or at least the common case instruction mix as possible. So let's see what these look like. Again, we are measuring CPI from when the first instruction finishes or enters write back to when the last instruction finishes or exits write back. So here's a few examples. This one is the same as from the previous slide. 3 instructions, 3 cycles, CPI 3/3 equals 1. This is the best case scenario. Typically, or unfortunately, when we have to deal with hazards, a common coping mechanism is to delay the execution of an instruction for a cycle while waiting for the hazard to clear. That in this pipeline slash, as I called it before, waterfall diagram looks something like this, where you can think about the delay as inserting a bubble into the pipeline stages that the later instruction, in this case instruction 3, would have occupied, and then you run instruction 3 when the hazard clears. And what that does, going back to the way we calculate CPI, is it introduces this dead cycle where something reaches right back, but it doesn't make any useful progress in the program. And so this, same as before, you just take the ratio 4/3 and you get your CPI greater than 1. And then you can just keep on doing this, and the idea is the same, and you keep on taking the ratio, and you can see how the more bubbles that you introduce, the worse you are in terms of CPI. Okay, so how do we resolve these hazards? So again, a structural hazard occurs when 2 instructions need the same hardware unit. You can resolve it through head-of-line blocking, queuing up the instructions that need it and pulling them out of the queue so that they can use the hardware resource one at a time. Another thing that you can do to always avoid these hazards is to add more hardware. So if you have 1 add unit and 2 instructions need to use it, you can queue them up, or you can just lay down another add unit and send them both to the 2 add units in parallel. This is called instructable. This is something you can do as a consequence of instruction level parallelism present in your program, which will be a major topic in a few weeks. The classic RISC-V stage integer pipeline has no structural hazards by design. So when you have a pipeline where instructions flow through all the stages, regardless of what instruction it is that we're executing, whether it's a memory instruction or an add instruction or something like this, you don't have structural hazards. You're kind of, by virtue of sending all instructions through all stages, which is kind of like doing dummy work, if you want to think about it that way, you're avoiding the structural hazard problem. So it's kind of like sneaking it under the rug, but it makes things convenient in terms of diagnosing what the remaining hazards are. Okay, next type of hazard, data hazards. So we have an instruction. It looks like this. 2 operands, 1 destination, RI, RJ, something, op, becomes RK. And the one that I think people are probably most comfortable with is the read after write hazard, where this phrase, read after write, refers to the dependent instruction needing to read a value that is written by an older instruction. And so we clearly can't execute the second instruction until the first one finishes because we don't know what the operand value is. And so sometimes we need to stall or interlock, as it's called. The next 2 examples. You probably heard about these in 61C. I don't think there was any incentive to internalize these next 2 examples aside from regurgitating them on an exam, because in the context of a simple pipeline like in 61C, it's a bit more difficult to understand why you should care. Anti-dependence, war hazard. That's interesting. When can this happen? What is happening? What's happening here is I have a later instruction which is writing to a register which is read by an earlier instruction. When can this happen? Yeah.
Before you're ready.
That's right, conceptually. So in the RISC-V style pipeline, or in the RISC-V pipeline that we're going to be discussing for the next few lectures, this is not a thing because you will not run into a situation, where a later instruction reaches write back before an older instruction. Because you remember, you have a diagonal waterfall diagram type shape where the order of write backs is consistent with program order. On the other hand, if you have a different pipeline where one instruction takes 5 cycles and another instruction takes 10 cycles, let's just say for argument's sake, then you can run into this nasty situation. Say the later instruction executes, I'll make it more extreme. Say this instruction executes in 1 cycle. Say this instruction executes in 10 cycles and doesn't read its operand until cycle 5 or something. If you have instructions that take variable cycle length to execute, which is kind of outside of the paradigm of pipelining as we know it, but actually not, then you can run into this nastiness. So, not really a thing with our current pipelines when we talk about out of order execution, where out of order means executing instructions out of order. And kind of by definition, you have to be very careful about how to deal with this. Okay, and so that I think is like, for whatever reason, between war and wa, so that's called a war hazard, a write after read. You have a later instruction writing before an older instruction reads a value. There's a third called wa, write after write, where you have, where's my thing here? Okay. You have 2 of the same register being written by 2 different instructions. And if you write this one first instead of this one first, then you're going to get the wrong answer because this is a stale value relative to this in program order. Short story, you get into pipelines where this can become a thing for similar reasons as war hazards, like if your instructions have variable length, and depending on where in the pipeline operands are read versus written in your pipeline, this can happen. In out of order execution, this is again a thing by design. We're going to be wanting to execute these potentially out of order, and so you have to be really careful about the order in which you actually update architectural state. For whatever reason, this one has always been hairier for me to kind of deal with conceptually. But hopefully by the end of this class, you'll have a ton of architectural knowledge on why we have to care about these things. But at least for the RISC-V style pipeline, the main offender is going to be the first one, raw hazards. Okay. All right. 3 different strategies for dealing with these hazards. 1, this word I used before, interlock. Wait until the hazard clears, which is to say, wait for an operand to be written back so that the next instruction can actually read that operand. Another solution, bypass. We'll see what bypassing means in a second, but at a high level, what it means is short-circuiting as soon as an operand becomes available in the middle of the execution of some instruction, short-circuiting that operand to a subsequent instruction. I believe that 61C covered this. Third, probably not covered in 61C, speculate, guess on the value, correct yourself later if you're wrong. This one's fascinating. We'll come back to it. Okay, interlocking versus bypassing. So this notation will take a little bit of getting used to so that you don't have an off by 1 error in your head. So let's just walk through the first one slowly. We're going to see a bunch of slides that look like this. So we have this add. It delivers data to a subsequent sub. So you have a raw hazard here. So here we have an add. Here's the fetch. And then we decode the add and we fetch the sub, or we try to fetch the sub. Nothing bad has happened yet because we're just fetching the sub. Then we execute the add and the sub is in decode. This is a problem. It's a problem because we don't have the result of the add yet, and it's decode where we need the result of the add. So what interlocking does is it introduces a bubble, and the way to kind of view this diagram, it's a little confusing, is that the fetch and decode on the next line corresponds to the subs execution. So this is a little confusing. You might be like, well, a cycle later, why doesn't something else like occupy the fetch stage? This is kind of a notational glitch in these diagrams that's not going to be important for getting the right answer, because what really matters is how many bubbles we need to introduce. But I just want to help people understand what this means. The fetch and the decode in the third row refers to just the sub. So the sub is stuck in decode. That's what this diagram means. And we just keep on doing this. We don't have any way of forwarding data yet from the add to the sub except through the write back stage. We're currently in we finally have arrived in the write back stage, and it's at the rising edge at the end of the write back stage that we can actually pass the data. And so that's when we pass the data. So the way to read this diagram again, we have 3 bubbles in the pipeline, and then finally we deliver at the rising edge here data to the sub, and we allow that decode to actually proceed. And that is how you draw the pipeline diagram for when the sub is allowed to proceed. So this is interlocking. And then you just keep on going. Bypassing is a more aggressive strategy that, like I described earlier, allows you to short circuit earlier the result of an older instruction to a dependent instruction. And the insight here, the beauty is that because of how the pipeline is designed, we have, namely that decode comes right before execute, we have that as soon as execute is done, that is, by the laws of physics, the earliest that we can possibly forward this value, because that is when it is produced. And it just so happens, because of this nice pipeline design, that that's exactly also the latest time when the dependent instruction needs that value. So it's the earliest time that we can forward the value, and the next cycle, when the subsequent dependent instruction is in execute, is the latest time that it can possibly get the value to compute the right result. And so we kind of slip it over to the next instruction, and we're able to execute these 2 instructions with no bubbles. Beautiful. How do we implement bypassing? Does anybody remember from CS61C? I believe you went over bypassing in 61C, how bypassing works. I have this diagram. What am I adding to this diagram to get bypassing? Any takers? It's exactly right. I couldn't have said it better myself. You add wires and multiplexers. Recall the diagram from the previous slide. Actually, I think, well, I'll just describe it this way. When the dependent instruction is in execute, the older instruction is in the memory stage, which means that its data is in this bank of registers here. And so we need to pull around a wire corresponding to the result of the add and feed it back into the input of the add, so that despite the fact that for the dependent instruction we read the register file twice, we're going to override the value that got read with the value that we actually want. If we want to bypass more aggressively for when instructions are not 1 apart, but 2 apart or 3 apart or however many apart before the older instruction exits the write back stage, we have to add more paths from more stages. So we can do this, it just comes at a hardware cost. Nominally, we'll be able to forward data from any older instruction to any younger instruction without incurring cycle bubbles. That's not actually true. There's an exception. We'll come to it in a slide or 2. That's the idea anyway. Last category. So we had interlocking, we had bypassing, we had speculation. This one's great. Rather than waiting for the value or short circuit bypassing the value, we can just guess what it is. What percentage of computation done today is with 0 operands, do you think? How many times am I doing arithmetic where 1 or both of the operands are 0? Turns out I'm doing it quite a lot, more than you'd expect. And for that reason, well, people looked at traces, simulation traces, and were like, wow, there's a lot of zeros here. And even if there's not zeros, maybe there's non-zeros, but they're very predictable. For example, if you're in a loop and you're looking at the add instruction which increments the loop index, You can either increment the loop index, or you can just design a little circuit which predicts what the next loop index is going to be, regardless of the add instruction that is actually executing on your behalf. And if you do this, it's like cutting one of these data dependencies, because you're shoving a value that you've guessed is correct into a subsequent instruction, and it's just executing on the assumption that that is correct. What happens, what's the kind of trade-off with speculation? Is it like a panacea? What's the kind of hard thing about it? Anyone? Yeah. If you guess wrong, you've done a lot of work that you didn't have to. So has anyone here taken computational complexity theory? One person. Okay, well, P versus NP. Speculation is an architect's take on NP, trying to implement a microarchitecture that looks more like an NP, a machine that can evaluate any program in NP efficiently, just with limited depth. But because no one's taken computational complexity theory, I'll leave that half joke on the floor. Okay, so we've gone through structural hazards, data hazards. Now for control hazards. There's a few cases to consider here. Like I said, these are both about waiting for an operand to become available, but one, namely control hazards, is about operands going into control instructions like branches and jumps. And this is worth breaking out into a separate category because it's needed much earlier in the pipeline, namely in the fetch stage, as opposed to like the execute stage. So let's case by case this a little bit and understand what we need. So we've got a bunch of different types of control flow instructions. We have unconditional jumps, we have jump register, the JR instruction, we have conditional branches, and then we have everything else. And each one of these things needs different information in order to decide A, if we're going to change control flow, and B, where we're going to go. So the condition and the target. Where does this information become available? So we have our pipeline here. And if we just walk left to right, the PC is known in the fetch stage. So if you ever need to do like a PC relative branch or jump, you at least have the PC, which is like your base, in your hand at the very beginning. The opcode and correspondingly the offset is known in the decode stage. So as soon as you decode, you know if it's a branch or a jump or whatever. And if it's a branch or a jump with an immediate, like a PC relative immediate, you can grab that immediate out of the instruction encoding. So you know that there. In the execute stage, you have the branch condition and the jump register known at different parts of the execute stage. So once you read out of the register file, at the end of decode, you have what you need for jump register, which just jumps to the contents of a register, like a function table. And the condition is known, at least for this microarchitecture, for this data path, at the end of execute, because the condition logic is implemented inside of the ALU. That is not fundamental, but it's just, we'll use this pipeline for example purposes. So the point here is that we need subsets of this information, and we know it at different points in the pipeline. And we need it very early on. And that's the crux of the challenge here. We don't know it until later, and we need it earlier on. All right, so what we're going to do is we're going to walk through just case by case what signaling we need and what bubbles it incurs to handle these different types of jumps. So we'll start with unconditional PC relative jumps. So this is a jump instruction that always goes to the target, and the target is given by the PC plus an offset, which is given in the instruction. So going back to the previous slide, we have everything we need in the decode stage. So we have the PC in the fetch stage. We know that it's a jump in the second stage, decode stage, and we know the offset, the immediate, because we get it in decode. And so the way that we implement this jump is, as soon as we know that this is a jump, we send our signal up to the controller, which says, hey, this is a jump, you need to redirect control flow. And the controller is going to send back down two signals. It's going to send a signal which kills the next instruction, because when the jump is in decode, the next instruction is not one that we actually want to execute because we are jumping at the point of that jump instruction. So we need to kill it, and we need to redirect the PC. We need to change what the next PC is going to be based on summing the PC of the jump with the immediate of the jump. That's what this add circuit in the decode stage is doing. So we're going to change the direction of that multiplexer. So we're going to change the direction of the multiplexer. We're going to flip a bit, which is called kill, and that's how we implement a jump. And just to say something about this kill signal. So we have the next instruction, which is not the right instruction, that will be writing to this bank of registers when the jump finishes decode. By inserting this kill signal, by flipping a bit called kill into the same pipeline registers as that instruction will be considered a no-op, a bubble. So that is how we implement bubbles in this pipeline. We snake back and we ram a kill signal into the bank of registers, which is responsible for that instruction. And so if we look at the pipeline diagram for this, we start with our jump. We decode the jump. We fetch the next instruction, which is wrong. We send the kill signal. That creates a bubble for that next instruction. And then we start fetching the target afterwards. And then we just continue executing the target and we're good to go. That's jump, or the most basic jump. Delay slots. This bubble is painful. How can we get rid of it? Well, there was an idea used in early RISC architectures called delay slot, where this is quite an idea. This idea says that at the level of the ISA, were delay slots discussed in 61C? Is that still a thing? Wow, no, yes, a little bit of controversy. I'm waiting for them to kill that idea in 61C and only actually introduce it in the later courses. The idea is to expose to the ISA a contract where whenever we have a branch instruction or a jump instruction, which we're doing the delay slot for, when we decide to redirect control flow, we're actually going to execute the next instruction in program order after the jump. So actually baked into the ISA is a contract which says, if you have an instruction after the jump, you're going to execute it. And that is part of the architectural semantics of the program. And only after that are you going to redirect control flow. And the reason for doing that is now you have some useful instruction potentially instead of a bubble that you have to insert. So the microarchitecture executes it, it does useful work. If you can't, as the programmer or the compiler, put an instruction there, you have to pad the space after the jump with a no-op. And you do nothing. So it becomes the programmer and the compiler's problem to fill that delay slot. And the whole point is so that in the common case, or what they thought was the common case microarchitecture for the ISA, that they would not incur this bubble when executing the jump instruction. This is not really a thing anymore because it makes a pretty low-level wrangly assumption about what the microarchitecture will look like at the ISA level, which an artist might call inelegant. But we'll see how it had been used in several contexts since then. Yeah, it's not used today. It encodes a microarchitectural detail into the ISA. It actually has performance downsides to it, which dominated the upsides. It turns out that instruction cache memory is sacred and you don't want to bloat your program. And if you can't fill these delay slots, you bloat your program with no ops. And so it's actually not great from a performance perspective sometimes. It also complicates, we're going to end on this slide. It complicates the design of more advanced microarchitectures. So this pipeline that we have here is single fetch. I'm fetching a single instruction per cycle, and I'm executing all the instructions in order. Pipelines today, like in commercial microprocessors, will fetch between 4 and 8 instructions per cycle. On average, 25% of instructions given a stock ISA are branches. So you're fetching multiple branches or jumps per cycle. And in fact, sometimes you'll be executing a branch immediately after. a branch. Say you're traversing some complicated data structure. You'll go branch, 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 branch. What happens when you're fetching multiple branches per cycle, having to redirect control flow for one or two or three or all of those branches, and you actually could even in the worst case have a branch in your delay slot? How on earth would you deal with that? It becomes kind of like this recursive paradox that designers did not want to deal with. And so they got rid of branch delay slots. Now what we use is branch prediction. And this kind of exemplifies why it's okay to keep the ISA clean. We've come up with so many cool ways to innovate the microarchitecture and kind of smooth out these rough edges that it's fine to keep the ISA simple, because the microarchitecture can oftentimes fill these bubbles with useful work, either through prediction or out of order execution or speculation or some other technique like that. Okay, that's where we'll stop today. We'll continue with conditional branches on Tuesday, and have a good weekend. Sure. Here, one second. Let me say goodbye to people.